This is my lecture, number 14. We will talk today about linear model following design for decoupling applications. I will show you how to build a linear model following system that would follow the model. And if you would choose the model to be a decoupled system, the resultant system will act as a model and it will be also decoupled. I want to tell you that this is the approach number 4 in decoupling control. Linear model following systems are used in adaptive control. However, in adaptive control, they're used only as the first stage in building an adaptive system. However, the results of linear model following design could be successfully applied for decoupling applications. Therefore, I originally did not include this topic in 462 material, assuming that you will face it later in adaptive control. But since some of you will take this 462 stuff or 510 material, and this will be your last course in controls, in this case, or because of this reason, I decided to include linear model following approach in our 462 material. I want you to note that linear model following design is not shown in your recent edition of the textbook. I will include it for the next year, and since this material is not part of the textbook, I am providing you with this write-up that you can download and use in addition to your text. It already is placed or has been placed on the My Courses. One way or another, let me assume that we have the state variable mathematical description of a multi-input, multi-output controlled plant. You can see the derivative of the state vector. You can see the fundamental matrix. Fundamental matrix is multiplied by the state vector. You have plus, you have matrix BP, and you have the vector of control efforts. But I have to tell you that when we do linear model following design, the number of state variables must be the same as the number of the control efforts. Otherwise, your design may not be achievable. Matrix C is a unit matrix, which basically means that effectively all those state variables that we want to be output variables, we can use as output variables. Since the number of components of the state vector and number of components of the control effort is the same, matrix AP and matrix BP they are both square and they have the same dimensions. The control plant is cross-coupled, and because of this, in order to have convenient, independent access to any chosen state variable, we have to apply some decoupling efforts. We have to introduce a decoupling control system. For our model, we have the state variable description. The order of the model is exactly the same as the order of the controlled plant. However, the model is decoupled. Effectively, this model is nothing but a combination of several completely independent systems described in the state variable notation. The next what we will do is this. We have to introduce a controller. And this control law is defined as follows. The vector of control efforts applied to the plant, and you remember the number of control efforts is the same as the number of state variables. The vector of control efforts is equal to some matrix Ku times the reference input plus my matrix Km times the state vector of the model minus matrix Kp times state vector of the controlled plant. And I want you to take a close look at this expression. This expression effectively represents the negative state variable feedback that will be introduced in this controlled plant. Matrix Kp is nothing but the matrix of the controller. We used to call this matrix matrix F. However, earlier we've been considering single input, single output systems, and matrix Kp used to be a row matrix. In our case, matrix Kp is a square matrix. It has the same dimension as the fundamental matrix of the control plant, and actually fundamental matrix of the model. Keep this in mind, and I will show you the critical moment of truth. Basically, we'll show you why we have to have a square matrix, Kp. Now I'm taking equation of the controlled plant, this equation, but the vector of control efforts, look, I replace by its definition of the controller. So I have matrix Bp should be multiplied by U. However, U is defined as Ku times reference plus Km times state vector of the model minus matrix Kp, the state variable controller, times state vector of the plant. And then after this is done, I can open parentheses and make this very simple algebraic transformation that each of you can easily perform on your own. And then I will introduce the error. This error is defined as the difference between the state vector of the model and the state vector of the controlled plant. Obviously, this error represents the discrepancy between properties of the plant and properties of the model. The next what I will do, I will define derivative of this error. Look what we do. Derivative of this error, error dot, should be equal to the derivative of the model equation, or of the state vector of the model, minus derivative of the state vector of the controlled plant. It's written right here. However, for the model, I have this definition of the derivative, and I'm writing it right here. Right here. So this part is nothing but derivative of the state vector of the model. And then I have minus sign, and I have the derivative of the state vector of the controlled plant. This expression I have with minus sign. So I have minus APX, minus BPKUR, minus BPKMZ, plus BP Kp times x. But then I am making a simple algebraic trick. I will add and I will subtract exactly the same term to this equation of the derivative of the error. This always could be done. And the term that I chose to add and to subtract is AM matrix minus BPKM times x. And then I have minus AM minus BPKM times x. So nothing changed in the equation for derivative of the error. The next what I have to do is to make regrouping of terms in the right hand side of this equation. So look what I have. I have 1, 2, 3, 4, 5, 6, 7, 8 terms, and I regrouped them. I have term AM minus BPKM times Z. I guess I use this and these terms. I have AM minus BPKM times X. I'm utilizing this term that was initially artificially introduced in the system. I have BM minus BPKU times reference. I'm using this term and I'm using this term. And then I have AM minus BPKM with minus in front of it. This is this term. So this is the regrouping that I have done. And then you can see that I can combine together this term and this term. AM minus BPKM will be factored out, and in parentheses I will have vector, state vector of the model minus state vector x. And then I will keep this term with the reference. And then I created this large term using this and using that with the state vector of the plant x. And finally, I will recall, and you should recall, that z minus x is error. This term is written without any changes, and this term is defined written without any changes. So I have to tell you that the error derivative equation now is written as you can see here. As you can see here. What should we expect of the derivative of the error? Derivative of the error should disappear with time, because error must disappear with time. This will happen. This will happen if for the derivative of the error I will have this matrix times the error, and this part will be zero. Then the equation for the error will look like equation without any forcing function. No forcing function, no motion in the system, especially if you have zero initial conditions. Or error defined by this matrix, which would be fundamental matrix of the error equation. Without this term and without this term will decay with time. And I have to tell you that this decay will take place only if all eigenvalues of this matrix AM minus BPKM are in the left-hand side of the complex plane. So this is the reality of life. What we have accomplished up to this point? I got for you equation for the error, for the discrepancy between the state vector of the model and state vector of the controlled plant. This error equation consists of some fundamental matrix times error, and then I have some additional terms. If I would make these additional terms equal to 0, then we will get exactly what we want. The error will be converging, and this convergence process will be consistent with the eigenvalues of matrix AM minus BPKM. So this is the nature of our design. Speaking of the matrix diagram, I want you to see the model. It is described by this state variable configuration. This is the state vector of the model. You see the controlled plant defined by state variable configuration. You can see matrix Kp that is used to form the negative state variable feedback around the controlled plant. You can see matrix Ku that works as a filter through which reference is applied to the input of the controlled plant. And you can see matrix Km that also works as a filter through which the state vector of the model is also applied to the input of the controlled plant. This is the configuration for a linear model following system. And I have to tell you that if I would turn these expressions into zeros, the state vector of the controlled plant will be following the state vector of the model. And if model is decoupled, so be it. We will have conditions for the creation of a decoupled system. The resultant system will be decoupled. You may have question, where is matrix C? Matrix C is very self-explanatory. It will be unit matrix in this case and unit matrix in that case. You know, matrix C, I want to remind you that this matrix C is used to define outputs of the system. And there is nothing wrong for a realistic system to use state variables as the output, especially if these state variables represent real physical signals. Some of these real physical signals could be utilized as the output variables for the system. So we have two equations to satisfy. The first equation says that Bm minus Bpku must be equal to 0. It works with this matrix Bm of the plant, matrix Ku that we introduced, and matrix Bp of the plant. The second equation is more complex. We have Am minus Bpkm must be equal, look, if this is 0, I can rewrite it in this form. Am minus Bpkm must be equal to Ap minus Bpkp. Look, what is Ap minus Bpkp? What is it? This is the control plant, and it has this state variable controller. So this equation, Ap minus Bpkp, is nothing but the fundamental matrix of the closed loop system, this system, that includes plant with the state variable controller, represented by matrix Kp. So yes, this is the closed loop fundamental matrix of the closed loop system. And now we can go over the design steps. Performing these design steps would inevitably lead you a decoupled behavior of the design system. First of all, and the best way for me to discuss this design would be to use a specific numerical example of a reasonably complex and at the same time reasonably simple controlled plant. This is matrix P of the control plant, AP, fundamental matrix of the control plant. This is matrix BP of the control plant. Don't be surprised, it is a square matrix. And this is a matrix CP. This matrix CP implies that the controlled plant has two output variables. We choose state variable x1 and state variable x3 to be the output variables of our control plant. First, what we want to do, we want to look at the description of the controlled plant. And you can easily realize that our controlled plant has a total of 4 control efforts. Well, by looking at the equation, you can realize that this controlled plant is cross-coupled, which means that each of these control efforts will be affecting all outputs, output number 1 and output number 2. And if you want to have an independent access to, let's say, output number 1, you have to be very, very tricky. You have to come up with a very special combination of increments for each of the 4 control efforts, which is far beyond human abilities. I also want to tell you that I took eigenvalues of the fundamental matrix, AP. And take a look at these eigenvalues. This is an eigenvalue in the right-hand side of the complex plane. This eigenvalue is in the right-hand side of the complex plane. So this controlled plant is not only cross-coupled, but it is also unstable. Now, first, we have to stabilize the controlled plant. And to stabilize the controlled plant, we have to introduce appropriate feedback in the system. And we want to have certain dynamics for the stabilized system. And I chose this dynamics. And this dynamics is represented by these 4 eigenvalues for the closed loop fundamental matrix. You can see that I am implying 4 seconds settling time, because this is the dominant one, a real dominant eigenvalue, and these eigenvalues are non-dominant. So be it. The closed loop system will have these eigenvalues. And then we would have to introduce a state variable controller. The state variable controller will turn this fundamental matrix of the plant into the fundamental matrix that has all the required eigenvalues. And to make our life simple, I will define the desired closed loop systems fundamental matrix in this form, consistent with the canonical controllable form definition. It's very easy to realize that this matrix A closed loop has exactly the eigenvalues that we intended for it. Now it is time to define the state variable controller represented by matrix Kp, and it will be based on the following equation. This is the desired fundamental matrix of the closed-loop system. I have it written right here. It is equal to the fundamental matrix of the control plant minus the state variable feedback. Now, this tells me that BP Kp matrix will be equal to matrix AP minus A closed loop. And now I can easily find matrix Kp performing this computation. BP in the power of minus AP minus A closed loop. It is very straightforward. And in order to do it, you need a software tool because it is a fourth order system. Now, obviously, this could be done only if matrix BP is a non-singular matrix. So effectively, right here, I am designing the controller, state variable controller for the system. Now you may ask me the following question. We used to convert system description into canonical controllable form. We used to define desired system by a canonical controllable form. We used to find the controller and then convert this controller from the canonical controllable form controller to the controller suitable for the arbitrary system that we had in the beginning. Why are we not doing this here? For a very good reason. The number of control efforts results in the matrix BP that has the same dimension as matrix AP. And because of this, when I perform this computation, I am getting a square matrix for the controller. This is the square matrix. It's written right here. Okay? And with the square matrix of the controller, I have the ability to obtain exactly the desired matrix, fundamental matrix of the closed loop system. Without a square matrix Kp, I would never be able to make sure that right-hand side in this expression is equal to the left-hand side. Okay? How we handle the situation, how we used to handle the situation earlier. You know, we were taking advantage of the canonical controllable form. With a row matrix of the controller, we should be able to handle only the last row of the closed loop matrix, fundamental matrix of the closed loop system. This expression enables us to handle the entire matrix, fundamental matrix of the closed loop system. If I would insert this definition of matrix Kp into this equation, I can assure you that in the left-hand side, you will get exactly the matrix, closed loop matrix, A closed loop. So this is something to think about. And it happens only because matrix BP has the same dimension as the matrix AP. It is time now to take a look at the design specifications and define matrix AM and matrix BM of the model. And this is what I'm doing right here. This is what I'm doing right here. For the model, I have independent block 1 and independent block number 2. Each of these blocks have canonical controllable form configuration. Matrix BM also has 2 independent blocks. And matrix CM is the matrix defining output variables of the model. Its configuration is consistent with the configuration of the matrix C of the controlled plane. If you will take a close look at these expressions, and since you remember the direct decomposition rules, and since you can perform this direct decomposition of a transfer function into state variable description, and since you know how to relate state variable description to equivalent transfer functions, please note that this combination of matrix AM, BM, and CM represent a system that has 2 completely independent second-order channels. For channel number 1, we have this transfer function. For channel number 2, we have this transfer function. And it's also important that if I would insert 0 instead of S, 0 instead of S, then G11 and G22 will be equal to 1, which means that these 2 transfer functions represent 2 closed-loop channels, 2 independent second-order closed-loop channels that we want to impose on our controlled plane. The next is the definition of matrix Km and matrix Ku, using these equations. Let me start from matrix Km. If you remember, AM minus BP Km must be equal to AP minus BP Kp. But AP minus BP Kp is our closed-loop system. It is the fundamental matrix of the closed-loop system, this one. So what we do now? We're getting AM minus BP Km is equal to a closed loop, which means that BP Km is equal to AM minus a closed loop. Or we have the ability to define matrix Km by performing inverse of matrix BP. And earlier we relied on this matrix to be non-singular, and I guess if it is non-singular, we have no problem with getting matrix Km defined. And this is the matrix Km, obtained using a software tool. So no problem. The next what we have to do is to define matrix Ku. We will get matrix Ku from this equation. Matrix Bm is defined. Matrix BP is matrix B of the control plane, 4x4 matrix, it is there. And Ku we have to determine. So BP Ku must be equal to Bm, and Ku is equal to Bm in the power of minus 1, BP in the power of minus 1 times Bm. I want you to realize that matrix Bm is a 4x2 matrix. Why 4x2? because there are 4 state variables in the model and 2 control efforts. And because of this, the result of our computation will be a 4 by 2 matrix KU. Our design at this point is complete. If you will take a look at the original configuration of the system, we have model defined, we have control plan given to us. The control plan was stabilized by introducing this 4 by 4 matrix. And then, based on the equations given earlier, we define matrix Km, which is a square matrix, and matrix Ku, which is a 4 by 2 matrix. The system is designed. And the best what we can do at this point is to implement this design in the simulation domain. I'm using my software vsim that may not be as good and as common as the Simulink. However, it is ideal for the teaching purposes, for making presentations. Look what we have. First of all, I want to show you the controlled plant. And I am using variables y1, y2, y3, and y4 to be state variables of the controlled plant. Look, there is a little bit of discrepancy. In my earlier definition, I said that x1, x2, x3, x4 are state variables of the plant. In my simulation setup that I already have, I use variables y1, y2, y3, and y4. What's the big deal? But the first state variable of the controlled plant, y1, is defined as first state variable times first element of the matrix A, second state variable times the second element of the first row of matrix A, third state variable times the third element of the first row of matrix A, fourth state variable times the fourth element of the first row of matrix A. So what is 5 minus 6, 7, and 4? They are elements of the first row of the fundamental matrix. Why the first row? Because my goal is to define the first state variable of the plant. And then I have 4 control efforts. Each of them is multiplied by the appropriate element of the square matrix B. The result of this is to be integrated. And I use it, define it, y1, which is the first state variable of the plant. And then I want to define the output of the plant, and this is the output of the plant. If you remember matrix C of the plant, this is the first output of the plant. It's equal to the first state variable. This is how I define the second state variable of the controlled plant. To define the second state variable, I have all state variables multiplied correspondingly by the elements of the second row of the matrix A, plus all control efforts multiplied correspondingly by all elements of the row number 2 of the matrix B, and so on. Here I have the state variable number 3 defined of the plant. I have all state variables of the plant multiplied by the elements of the third row of matrix A, and all control efforts multiplied by the elements of the row number 3 of the matrix B. In a similar fashion, I define the state variable of the plant number 4, but I want you to note that the state variable number 3 is designated to be the second output variable of the plant. So the plant has first and the second output variables. And they are, of course, cross-coupled. Look, imagine applying some kind of excitation to this input. Obviously, the output number 1 and output number 2 will be affected. Yeah, this is the slightly altered matrix diagram of the system. This is the model. This is the model. And for this model, I'm using X as the state vector. This is the controlled plant, and for the plant, I use variables Y as components of the state vector. And I'm not showing here matrix C. It is time for me now to define the state variable feedback. The state variable feedback is represented, I call it vector V. This vector V is applied to the input of the controlled plant, and it's equal to appropriate matrix Kp, or matrix of the appropriate controller. So this is the state variable feedback. So what do I have here? I have all state variables of the control plant multiplied by the first row of the matrix Kp. Kp is a square matrix. And what I have is the first part, the first component of the state variable feedback. I call it V1. All state variables of the plant multiplied by the elements of the row number 2 of the matrix Kp. This is the second component of the state variable feedback, and actually this is the component number 4. The next, what I have to do is to build the model of our resultant system. This is the model. For model, I use state variables x1, x2, x3, and x4. So please don't be, I'm not using variable z as I initially suggested. I'm using x1, x2, x3, and x4. Because I'm using a simulation setup that was developed earlier. And what you can see here are elements of the first row of matrix A of the model. Don't forget that matrix B of the model is a 4x2 matrix. So none of these control efforts, or here they are reference signals, none of these reference signals affect the state variable number 1 of the model. And this is the output of the model defined. This is the second state variable of the model. All state variables multiplied by the elements of the row number 2. And only reference number 1 affects the state variable number 2 of the model. And again, this is a setup which is very consistent with the mathematical results that were shown earlier, with the definition of matrix A of the model and matrix B of the model. The next what I do is, this is the block which represents some kind of vector h, it is km times x. Km times x block. But I have to give some name to the vector equal to this product, and I call it h. These are 4 state variables of the model multiplied by the elements of the first row of matrix Km. All state variables of the model multiplied by the second row of matrix Km, and so on. This is how I'm getting 4 components of the vector h defined as Km times x. And finally, it is time for me to define the controller of the system. The controller of the system is responsible for generating 4 control efforts of the controlled plant. To define these 4 control efforts of the controlled plant, I have reference number 1, reference number 2, multiplied by the first row of matrix KR. And then I have this state variable feedback injected, and I have one of the components of the vector Km times x. So this is the control law. The control law has 2 inputs, reference 1 and reference 2, and it has 4 outputs because the control law is responsible for generating 4 control efforts applied to the input of the plan. And when all this is done, first of all, I want to summarize my results. This is the controlled process. It has 2 outputs, output 1 and output 2. It has state variable feedback. You may ask me the question, how the state variable feedback contributes to the controlled process? It looks like they are isolated. They're not, because they communicate through internal variables. So I have to create separately state variable feedback minus Kp times y. Then I have to build block Km times x. And this is the reference model. And this is the control law. And please take a look. I am applying unit step to the input number 1 of the system, and obviously through the control law block. And control law block corresponds to the control process through internal variables, as well as state variable feedback, block KMX, and the reference model. They all interrelated through internal variables that you do not see in this picture. So there is nothing to be surprised. I'm applying unit step to the input number 1, and take a look. I have response only in the output number 1. There is some numerical noise in the output number 2, but it is negligible, and it is indeed numerical noise. When I applied unit step to the input number 2, I have response only in the output number 2. The settling time, the overshoot, is consistent with the design specifications. The output number 1 does not show anything but numerical noise. We're done with the system design. And this is not the last time you're looking into the system design, because this type of design will be given to you in your take-home project. So you will have to go through every single simulation setup in order to master this type of design, of decoupling design, providing, of course, that you're interested in getting a good grade. Right now, I want to give you a demo on steady-state decoupling control. because I'm about to close this topic on decoupling control. And the best way to close a topic is to provide you sufficient information demonstrating the appropriate technologies. So listen, this is a 2-input, 2-output controlled plant. We're doing steady-state decoupling control. In steady-state decoupling control, it is assumed that this transfer matrix represents system with a number of local feedbacks. So every component of the system is stable and is expected to have acceptable settling times. The only problem is that if you would apply input or step, let's say, to input number 1, you will see a response in every output of the system. The system is coupled. This is the description of the system, 2-input, 2-output system. Outputs are Y1 and Y2. These are the elements of this transfer matrix, and these are the control efforts. I want to write it only for the purpose of simulation. I want to remind you that now the output 1 and output 2 are defined through input 1 and input 2. Input 1 and input 2. And I want to show you how I simulate this result. This is the simulation setup for the original controlled plant. And clearly you can see here that input number 1 affects output number 1, and the same input number 1 affects output number 2. Cross-coupling takes place. Now I want to define the decoupling filter, and you know that the decoupling filter is to be defined, and I call it W filter, with elements W11, W12, W21, and W22. To define this filter, I have to take the original transfer matrix of the plant, replace S by 0, and take the inverse. This is the original transfer matrix of the controlled process. When S is equal to 0, I raise it into power of -1. This is the result. So this is the decoupling filter W. And now what I will do, I will define control effort U1 and control effort U2 through the decoupling filter properties and the external reference 1 and reference 2. With respect to reference 1 and reference 2, the system will be decoupled. With respect to U1 and U2, the system is not decoupled. So look, for the purpose of simulation, I want you to see that U1 now will be defined as W11 times R1 plus W12 times R2. And similar for U2, where U2 and U1 are control efforts applied to our process. And now I'm implementing the coupling filter. The coupling filter gives you U1 and U2 following this formula, and the system is tested by simulation. First of all, I'm not using the coupling filter. I want to show you that the controlled plant is a cross-coupled plant, or control process is cross-coupled, applying input step to input number 1, and you see 2 responses of the control plant. If I would try to manipulate independently output variable, this output variable y1, I probably will have to work with 2 inputs, and I would have to be very tricky in coming up with a combination of increments on input 1 and input 2 that would make desired change in the output 1 and make no changes in the output 2. However, If I would use the decoupling filter, it will happen automatically, effectively, without any undue intellectual efforts of the process operator. Look, I'm driving my system through the decoupling filter. I applied step to the input number 1 of the decoupling filter. This step is converted into 2 steps in the inputs of the plant. And look what happens. In the combination, these 2 steps applied to the input of the plant will make the independent change in the output number 1. But this change takes place only in the steady state. In the output number 2, you also can see some transient process, but in steady state, there is no impact on output number 2. Yeah, the coupling does work. And if I would make test the second input, with the second input, I'm applying step to the decoupling filter. In the output of the decoupling filter, I have 2 steps applied to input number 1 and input number 2, not unit steps, but properly strategically chosen magnitudes of the steps will take place. Now look what happens. As you apply these 2 inputs to the plant, you can see responses in both outputs. However, in the output number 1, in the output number 2, I will have the required residual change. Residual value is equal exactly to 1. In the output number 2, the transient process settles down and there is no residual changes could be detected. The system works, and I guess you will have to be prepared to simulate the system. I want to do now a presentation on full decoupling control with the use of state variable controller. I want you to realize that although full decoupling is done on the basis of transfer matrix of the system, eventually you will achieve the decoupling effect and you will have to stabilize the decoupled channels. How to stabilize the decoupled channels? Earlier, I showed you that you can do it by the introduction of a feedback controller. In this example, I want to show you that a state variable controller could be introduced to stabilize each of 2 decoupled channels. So listen, I'm using exactly the same controlled plant as you saw earlier. It is represented by a transfer matrix. I'm doing full decoupling. I have to come up with a filter, decoupling filter. I call it filter H, decoupling filter. And you know that this decoupling filter could be defined as an adjoint matrix. By the way, there should be an adjoint matrix of GS. And I'm using a software tool. So look what I do. In order to define transfer matrix H, I take the inverse of the transfer matrix G, and this inverse I multiply by determinant. Why I'm doing so? Because my software does not give me an adjoint matrix, but software gives me the inverse. And inverse, as you know, is equal to adjoint divided by determinant. So if I will take inverse and multiply it by determinant, I will get the adjoint matrix. after you will perform this operation, you will get a really horrific expression for matrix H because of numerical noise. And the next what you have to do would be to cancel poles and zeros in this horrific expression and get simplified definition for the matrix H, for the adjoint matrix H. And this is the adjoint matrix H defined. Did I really have to go through the computer tool? Probably not, because I know how to get a joint for a 2x2 matrix. Look, these two elements will exchange their positions, diagonal elements, and off-diagonal elements will stay where they are, but will get opposite signs, and you're getting the adjoint. However, there is a good reason for using computer tool, because at some point I will have to obtain matrix Q that is equal to matrix G times transfer matrix H. Q describes the decoupled system. And I also know that this Q will be a diagonal matrix, and this matrix Q will have two diagonal elements equal to determinant of this original matrix, transfer matrix of the control plane. So in order to compute the determinant, you will be better off with using the software tool. And this is expression for the determinant of the original transfer matrix. All right? So this is expression for the determinant. It's a fifth order system. It's not that easy to handle without a computer tool. And then I represented the same determinant in a pole zero form for a very good reason. I want to make sure that I do not have right-hand side zeros, and I don't have to use the Diophantine equation, because my next step will be to treat this diagonal element as an independent control plant and stabilize it, come up with a controller to stabilize it. No right-hand side zeros, and we can proceed. I want you to take a look at the decoupling filter. In our decoupling filter, HOS, there are two inputs, V1 and V2, and those are elements of the decoupling filter implemented in simulation tool. The next what I want to do, I will concentrate on elimination of zeros of the controlled plane. Why do we have to eliminate zeros? We have to eliminate zeros for two reasons. First of all, we want to have full control over the system overshoot. And this is a respectable reason by itself. But then there is another reason to eliminate right-hand side zeros. Do you remember that in order to determine matrix K of the state observer, we will be better off with eliminated, cancelled zeros of the control plane. And since I want to eliminate, to cancel zeros of the system, I can do it by introducing this filter. This is additional filter. And this additional filter will be introduced in series with the decoupling filter. And you can very easily see that this filter has two inputs and two outputs, and it has two absolutely independent channels. Each of these channels has transfer function equal to 1 divided by the numerator of the appropriate diagonal transfer function of the decoupled system. So let me show you. After the decoupling filter was introduced, our system could be viewed as two absolutely independent fifth-order systems. These are the polynomial denominators, and these are the polynomial numerators. Now, we will cancel polynomial numerators in both transfer functions QoS. Therefore, here, variables v1 and v2 will be created by this filter. And this filter, as you can realize, will cancel zeros of the plant. Now I want to test what we have done so far. This is the original controlled process. It was coupled. After we introduced the coupling filter, the combination of these two blocks turned into two completely independent fifth-order systems. However, each of the channels of the system, each of the system had zeros. When I placed another filter for the purpose of cancellation of zeros, I'm getting two fifth-order channels without zeros. What shall we do now? And look, I'm just showing you this reality. The resultant system is decoupled. I applied step to the input number 1. You will see response only in the output number 1. Now it is time to design state variable controllers. Because we did the coupled system, we have eliminated zeros. But as you can see from the simulation, the dynamics and the steady state values are unacceptable. We have to change dynamics, we have to change steady state values of the responses. And by doing so, we have to use a special state variable feedback controller. Because we decided to use state variable feedback controller, we could use a conventional controller. One way or another, we will use the state variable controller. For the state variable controller, we will define eigenvalues of the desired closed loop fundamental matrix of the system. We want undershoot under 5%, we want settling time of 4 seconds, we want settling time of 1 second, we want overshoot under 5%. How to handle the situation? These are two complex conjugate dominant poles. Surely they will assure 1 second settling time. And for non-dominant poles, we will choose these 3 poles. So we have total of 5 poles or 5 eigenvalues for the system. 2 dominant and 3 non-dominant. And if this is the case, we can easily get the desired characteristic polynomial for the closed loop system. And we know how to convert desired characteristic polynomial into the resultant fundamental matrix of the desired closed loop system. And you do this type of things by inspection. So the desired fundamental matrix is defined. Now it is time to take a look at the transfer, at the fundamental matrix of the controlled plant, or what we call controlled plant. We can get its fundamental matrix by inspection. Yeah, this is the denominator of the controlled plant. It's not controlled plant actually, but we treat it as a controlled plant. And by inspection, we can get its fundamental matrix. We have a very well established formula for computing matrix F of the state variable controller. It is 0, 0, 0, 1 times AP minus A closed loop, and we're getting this result. So this is the state variable controller that, being introduced, will enforce the desired dynamics on each of the decoupled channels. The only problem with this is the following. The state variables of the canonical controllable form and the general state variables for the decoupled channels are not known, not available, and therefore we will end up designing a state observer. Designing a state observer. Before we will proceed with the state observer, I would like to check the closed loop system transfer function. The state variable controller was introduced, and I want to see how the resultant closed loop transfer function for each of the channels will look like. I'm using this formula to define the transfer function for the closed loop channel number 1. This is matrix C. Don't be surprised, the zeros of the plant are cancelled. So this is matrix C of the system with cancelled zeros. This is unit matrix times S. This is matrix A of the plant, fundamental matrix of the plant. This is matrix B transposed. Well, this is matrix B. I wrote it as a row, but there is a transpose sign, times matrix F. And it is multiplied by matrix B. Again, it's written as a row, but there is a transpose sign. So this is the transfer function of the closed loop stabilized dynamic channel. What is missing? What's missing is this. If I would apply reference equal to 1, the steady state value of the response will be 1 over 170,425, which is no good. It's supposed to be also 1. So I can easily fix this deficiency by introducing this gain in the reference channel. So what you can see here is the control law for one of the decoupled channels. This is the state variable feedback, state variables x1, x2, x3, x4, x5 multiplied by the element of matrix F of the state variable controller. I insert minus sign, and this is reference multiplied by the constant gain, this constant gain. So this is the state variable controller. And as I said earlier, the problem is that x1, x2, x3, x4, and x5 are not available to us. And therefore, we will end up designing a state observer. We will design state observer by first defining desired eigenvalues of the fundamental matrix of the observation process. And if you remember, the observer should work at least twice as fast as the controller loop. And therefore, I will use this set of eigenvalues. In this case, well, you can notice that every real part is multiplied at least by a factor of 2. So this is the set of eigenvalues for the fundamental matrix for the state observer. And of course I can convert it into the associated characteristic polynomial. I would say I need a tool for this, software tool. But then, by inspection, I can get for you the appropriate fundamental matrix. And when this is done, we have to use my recursive formula to compute elements of matrix K, K1, K2, K3, K4, and K5. And this recursive formula is usable only because the zeros were cancelled, because of the specific configuration of matrix C. After this K1, K2, K3, K4, and K5 were established, I assemble them into a column matrix K. And this is the column matrix K. How to make sure that the result is correct? I will build matrix AK, the fundamental matrix of the observation process, equal to AP minus K C, but matrix C here is matrix C for the plant with cancelled zeros, A minus KC. But matrix C again reflects the fact that zeros were cancelled. Matrix K is known. Matrix AP is defined for the control plant. And I got this matrix. The only what I want from matrix, fundamental matrix of the observation process is that it has the desired eigenvalues. So I got this matrix. It's not canonical controllable form. It's basically an arbitrary form. But I got the eigenvalues for this matrix. And they are equal exactly to what they were supposed to be equal. Minus 8 plus minus 1j, minus 40 plus minus j, and minus 45. Perfect. This means that the observation process will converge twice as fast as the control loop. Now we can implement state observer in the simulation environment. And what's written here is very consistent with the definition of the state observer. I don't think I have this expression for state observer, but state observer has fundamental matrix A minus KC. It also has matrix K times output Y of the controlled plant, and it also has control input times matrix B, or matrix B times control input. And this is what I have. It's very self-explanatory, and when time will come for you to repeat this type of design, of course you will be looking at these results very, very carefully, providing that you're interested in getting a good grade. Finally, I can test the entire design system. This is the state, let me start from the controlled process. And then I have the decoupling filter. And then I have a filter intended for cancellation of zeros. And what I have now is a fully decoupled system with this input and this output and this input and this output. And then I want to do is to add the state variable controller and the state observer. I want you to keep in mind the state variable controller and state observer, they are interfaced with these dynamic blocks, but they are interfaced through internal variables. So you don't see these numerous hairy connections between these dynamic blocks. And when this was complete, I applied step reference to the input number 1, and this is what you can see. The response could be seen only in the output number 2. The settling time is what it's supposed to be. The overshoot is under 5%. At the same time, the second output does not show any response. Now I want to show you the beauty of independent access to individual outputs. Look, the second output, I want to be defined by a unit step reference. So it's supposed to undergo the transient process with the required settling time, required overshoot, and then it should yield the steady state value equal to 1 because it is driven by a unit step reference. For the second input, I use the sinusoidal signal. Okay, since I am not getting out of the beyond the bandwidth of the design system, you're supposed to have almost perfect sinusoid in the output. And this is the almost perfect sinusoid in the output. So look what I did through the coupling control. The first input I forced to follow a sinusoid. The first output of the plant I forced to follow the sinusoid. And the second output I forced to respond to a unit step reference. Independent access to individual channels.